the first lecture of this course on small-scale intensified two-phase processing. And myself, Professor Panagiota Angeli, or Yota, and Professor Sumana Ghosh will be delivering it. I am from the Department of Chemical Engineering at UCL, and Sumana is from here, from IIT Roorkee. So what I have done is I have a couple of slides to kind of introduce the, let's say, the course and myself today. But before that, this is a summary of what we are going to be doing. And Professor Ghosh also went through this table of contents, let's say, of the course. And the idea is that today I will cover these first two topics. First of all, an introduction to small-scale intensified processing. And then we will go more into discussion of flow patterns, two-phase flow patterns. And I will also cover a few things about pressure drop. How do we calculate pressure drop? The main emphasis, at least from the part of my lectures, is on liquid-liquid two-phase flows. But while I'm discussing these two things, I will also mention some information, bring in some information on gas-liquid flows. And then you see there is the topics kind of follow. So we will then talk about the effect of physical properties on hydrodynamics. And this to happen tomorrow. And I will start discussing about measuring techniques on two-phase flows. And from what I know, there is also a lab for some of these techniques, especially on imaging. And continuing, not just physical properties, but you will also, Professor Ghosh will also mention the effect of weightability on the hydrodynamics of these liquid-liquid flows. And I will follow up with this drop formation and effects of interfacial phenomena. This is droplet microfluidics. And the last of the course will now go into this intensified processing. First of all, we will look at intensified mass transfer into phase flows in small channels and scale-up issues. Okay, we do things in small channels, but how do we actually increase the production if we want to do more? And again, Sumana, Professor Ghosh will discuss reactions and the influence of surface properties on mass transfer. So a few things before we continue and how these things all were brought together. I am from UCL. I don't know if people have been to UK. UCL is I have a map as well, located very centrally. It was founded in 1826, and in 2 years' time, we are going to have our 200 years anniversary. And it was the first to admit students, regardless of class, race, or religion. In the old days, we had the big universities, Oxford, Cambridge, and some others in the north that were all based on religious, let's say, admissions. And it was the first to admit women students on equal terms with men. And it offered the systematic teaching of medicine, law, and engineering in England. So, yeah, a map, that's a bit of London, that's Thames. The university I showed you is located here, very close to the British Museum. But we also now have a new campus in east of London, UCL East, where the Queen Elizabeth Olympic Park is. If you watch the London Olympics a few years ago. And this is what we call UCL East campus. And here is some facts about it and some photographs. That's the outside of this new building, Marshgate building, where we as engineering and chemical engineering have labs and some different images. And some details of what it contains. It's 8 floors of high-tech cross-disciplinary research labs. The whole idea of what we developed there is to actually not to have departments, new departments or transfer departments, but to have interdisciplinary labs. And we are helped because the UCL Institute of Making is also located there. And the archetypal metal sculpture is also, this is a characteristic of this part of London. So the UCL Faculty of Engineering has a number of departments. We are chemical engineering, And this is the other disciplines, the other departments we have. We have a different department for biochemical engineering, but also computer science, civil, environmental, geomatic engineering, electrical engineering, mechanical, medical physics, security and crime science. And also this one is more of a unit rather than a department, science, technology, engineering, and public policy. We'll be discussing these things towards the end, how we fit what we offer as solutions. They also have to be socially acceptable and to address societal issues as well as environmental or energy issues. And we have the School of Management. So the there's a bit of yeah, okay. So are we right? Yeah. So the UCL, the chemical engineering department at UCL, was the first chemical engineering department in the UK. And a little bit of history on that. It was 100 years ago. And actually, this last academic year, we celebrated our centenary. And it was founded in memory of William Ramsay. Sir William Ramsay, he was a UCL chemist and discovered the noble gases, and he won a Nobel Prize for that. But he was also very much interested in the industrial application of chemistry. So there was this memorial fund to create a chair of chemical engineering, but also a department later on of chemical engineering. And now in the departments, we have these research areas, multi-phase systems, catalysis and reaction engineering, molecular and engineering thermodynamics, electrochemical engineering that do a lot of work also on fuel cells and batteries, and nature-inspired engineering. So multi-phase systems is where my research area belongs. And this is something like a general information about the department. This is the degree courses we offer, the 3-year BN, the 4-year Bachelor's of Engineering, and the 4th-year Master's of Engineering. And these are some of the MSc courses we offer. The traditional chemical process engineering, global management of natural resources, but some new ones as well that we developed because of our expansion to UCL East. Advanced propulsion, manufacturing of advanced materials, nature-inspired solutions. Just to give you an idea of the size of the department, we have about 555 undergraduate students, 122 MScs, about 200 PhD students and research fellows, PDRAs. And at the moment, we have 33 academic staff and 18 lecturers teaching. So within this, and now I'm coming more into what we are going to discuss today, within this multi-phase research area is where my Thames research group sits. And the work we do in my research group is actually looking at different scales, traditionally starting from larger scale to phase flows, originating from the old energy, oil and gas applications, moving as we go to medium and to small scale, that is actually linked to intensification, where we see the connecting, let's say, the connection between these all these scales is the interfacial phenomena. We are studying mainly liquid-liquid flows, and the effect of the interfacial phenomena are very important. Actually, small scales help us understand interactions, but can also be applied to large-scale flows. So, and that's a photograph from my research group. That's the front of UCL, a nice sunny day. If people have been to conferences, you might have come across some of them. Hopefully, we'll see you yourselves in some conferences in the future. And this is all the organizations that have been supporting the research. And some of it I will be showing to you here today. So if I go now to my first lecture, it's called Introduction to Small-Scale Intensified Processing. And I decided to talk a little bit first about this process intensification. I don't know if I can move that. Yeah, I can put it here. I'll hide it. Okay. Right. So why do we want to, and why do we want to actually, why we are talking about process intensification in small scales? So first of all, where did microscale come from? And I have a little bit of a history here. So let's say in the late 60s, a lot of silicon wafers started developing, and not just that, but we started having the integration of sensors into wafers, and that created what we call microelectromechanical systems, the MEMS. And these things exist and are widely used today. We can find them in cars, in printers, in biomedical devices. The whole concept then continued into applications to chemistry. And that's why when in the late 70s, we started having the microanalytical systems, MTAS as they are known, micro total analysis systems, as alternatives to just chemical sensors. You had a pH meter, for example, or more bulky devices. So in these MTAS, microanalytical systems, applications such as DNA sequencing, drug screening were started to be happening, to be performed. And later on, coming to where we are more or less now in the 90s, these MTAS were combined with precision engineering, not just wafers anymore, and microfabrication to lead to what we call microreaction engineering. So it was not just wafers that were developed initially and were mainly used in these MTAS, but we are now looking at different devices fabricated in different ways to actually have our microengineering micro devices for chemical engineering applications. And these devices, let's say, these units allowed chemistry, but also allowed the intensification of the processes. So we could use those to do high throughput screening. We could check large number of, let's say, properties, drugs, or whatever we wanted. Also do a lot of experiments quite fast without using a lot of materials. But they have also been used or applied to process intensification, not just as a way to do analysis, but as a way to actually start thinking about production. And the good thing is that in this case, by considering process intensification, this is what we will be discussing in the next slides, we can integrate into these micro devices sensors. And so at the same time, we also have this faster analysis and online monitoring. So the concepts now develop like this. Once we reach this fast analysis and online monitoring, we start talking about digitization of operations. And this is now the new concepts we are discussing, which is digital operations, digital twins, that are actually depending on these ones. We have fast analysis, fast readings, online monitoring, and of course, combined with modeling. So let me see. What are the benefits? This was the history of these microscale applications, let's say. What are the benefits, though? And I think if people have been working in this area, I don't know if I should try to have that a bit more interactive. Why do we want, I don't know if anybody in the room, I know some people are working. What do you think are the benefits? Why do we want to do operations or processes in small scales? I have some here, but I don't know, why did you decide to work with these small scales? Yeah?
Probably efficiency is much better at that level.
Yeah, efficiency is a step further. What is better efficiency? Excellent. Sorry? High surface area to volume ratios.
Good particle undergo same kind of treatment.
That's good, yeah. That's a nice one. Anybody else? All of the above. Okay, there are a lot of benefits. We are working in small scales, so the fluid films are thin, which means heat and mass transfer rates will be faster. They don't have to go through a lot of fluid. The films are thin. There is a disadvantage on that. We can discuss that later. Thin fluid films, enhanced heat and mass transfer rates means that we reduce the concentration and temperature gradients. The conditions are more uniform. And also, if we have a lot of increased surface to volume ratio, and also if we have more than one phases, if we increase the interfacial area, the specific interfacial area, the interfacial area per volume, which means that if we have interfacial phenomena, interfacial mass transfer, this is also enhanced. We have more surface area. Another benefit is that is obvious for two-phase operations is that we have this importance of increased importance of surface and interfacial forces. We'll discuss that in terms of dimensionless numbers in a minute, but gravity is not important anymore. Inertia is not as important, so surface interfacial forces become important, and this has a subtle, let's say, advantage, but it allows us to manipulate the flow patterns better than in large-scale systems, and we'll discuss about flow patterns in the afternoon. And so we have all these nice, well-controlled flow patterns. It's because we have this increased importance of surface interfacial forces. Because of all of the above, faster transport rates, uniform conditions, we can have better conversions, mixing is better, and selectivities, and this brings back to efficiencies effectively, and of course, reduced waste. If we have particular chemicals, we have safer operations, much more less material to deal with, less non-uniformities, which can bring in temperature, for example, that can bring unsafe conditions. One good thing as well is that we're talking about slow flows, small, not slow flows, small systems, small characteristic dimensions, which means Reynolds numbers are not very high. Flows, because of that also, because of the high large interfacial forces, the flows are also well defined, and that enables modeling. Couple of disadvantages. I mentioned all the good bits, but what are the disadvantages of actually working on small scales? Yeah, okay. Yeah. Sorry? Yeah. Anything else? I had one more. Low throughput, high pressure losses.
So much dominated over the
Yeah. So basically all our flows tend to be laminar. I should have added here laminar flows actually somewhere. Goes up here. We lose the advantage of turbulence. It's a good and a bad thing. Actually, because we have very thin films, it means the mass transfer by diffusion, heat or mass transfer by conduction or diffusion is fast. But of course, we lose all the advantages that we get from turbulence, which is the fast mixing. Not having to deal with turbulence means that our modeling is easier. It's much more easy if people have done CFD to model laminar flows than to model turbulence. But these are added disadvantages. And the throughput, somebody mentioned it, is also quite important. So that's why these later lectures will be interesting. So a lot of people say that, okay, we have a lot of advantages of working in small scales, but actually, can we bring it up to production level? Or is this unrealistic? Definitely, we can use them for analysis because of all these advantages. I think somebody mentioned it. One of the advantages they were suggesting is that you give all the molecules, let's say, the same experience because the residence times are better defined and a lot more controlled. Let me go right now to have this definition of microscale, slightly having some equations. So what is small? We say micro, small channels, but what is actually small? It's a little bit of a vague, let's say, concept. So the main, let's say, way to say that check to if a channel is small is to see if the surface tension forces dominate over the gravitational forces. That's the primary thing we would be looking at. What does that mean? This means that this dimensionless number, I will go to it, which is the ratio of gravity or buoyancy forces over surface tension forces, has a small value. We want these forces to dominate over these. There are a couple of ways this dimensionless number appears in the literature. Bond number is quite common. Some people call it also Eötvös number, but this is what it is. This is this ratio. We have gravity and we have surface tension or interfacial tension. Okay. If we talk about gas liquid systems, is surface tension, liquid systems is interfacial tension. And now, okay, we have this number. The forces will be about equivalent if this is about 1. But when do we actually lose the significance of the gravity forces? And there are various suggestions in the literature. And in all these things, I also give some paper references, journal references at the bottom. I don't know if you will be having access, I believe you are going to have access in the end in the slides. So various people in the literature have suggested various values. So this is some range. So they said the bond number has to be either less than 0.88 or up to this value. If we try to apply that to air-water flows, this means that we are dealing with channels between 2.6 and 17 millimeters. So even a channel of 17 millimeters can be considered small, or a channel where the gravity forces may not be important. Again, you want to see a lot of literature with people working on 17 millimeter channels and calling them microscales. So most of the literature is around this 1 to 2 millimeters as an upper limit. And this is actually important. And this is where you should start thinking yourselves as well. We talk about micro, but we also have to be thinking what do we want to do with our small channels. Small channels are nice. They involve a lot of microfabrication material. Where is the benefit of actually using them? And if the application, if our interest is to do fast analysis, we may be thinking, okay, we can go very small because we want to reduce the number of the amount of material used. It's much more safe, much more easy. If we want to start thinking about production, though, it will be quite tricky. Channels that are sub-millimeter. Okay, so we really need to be clear or what we want to do with these small channels. In that case, if production is what we are interested in, then we should be pushing, let's say, the size, because otherwise we'll have problems with high pressure drop, low throughput. Yeah.
Phone number when it is 1 by equals.
Yeah, so this when it's 1, it says dimensionless numbers are ratios of forces. They're not exact numbers. So it shows you the relevant significance. So you would say that the forces are equivalent, about similar, when this is about 1. What we want to see is when, and I will have a map in a minute, when gravity forces are not significant. So the smaller the better, let's say, but how small is small? Yeah, and these are some of the values that the literature has proposed, that you don't see the effects of gravity when they are smaller than these. Well, different values in the literature, that's what I'm trying to say.
So that is dependent on the system we are dealing with.
Exactly, of the two-phase system or the single system, because you have densities, you have viscosities, you have a lot of, yeah.
So is it possible in the same with transient from without no effect to the effect in the same system?
You start increasing the size of the channel, for example, yes.
Or due to process condition?
That's what it affects. The size of the channel, I should have gone through that. This is the density differences between the two phases. This is the gravity, and this is the channel size, and this is the surface tension.
So surface tension and the gravity, if the due to process is changing along the length, is it possible to transfer?
Yeah, but you cannot change gravity and surface tension along the length. It depends on what, yeah, exactly. So if you have or air, water, the only thing here that can be affected, unless you change the pressure, so the density of the air changes, yeah, or the temperature or something else. Yeah. Otherwise, it would be for constant fluids, it will be the, yeah. And actually what this paper, White and Barrymore paper, is quite old, but it's a very nice graph where they basically plotted the bond or Eötvös number against this, they plotted the Eötvös number against this dimensionless number. And what they find out, this is the Froude number here. And what they showed is, this is a nice graph in an old paper. I will stay only on one thing, that the bubble does not rise in a vertical capillary when this bond number is less than 4. So for them, this is what defines how they define this effect of gravity being diminished. So they said, if my bond number is less than 4, I'm in this region of the map, the bubbles will not rise automatically, which means gravity is not important anymore. And they suggested it as a criterion. So have that in mind. We will talk about plug flow, Taylor flow in other lectures, subsequent lectures. We can have, if people have worked with two-phase plug flows, Taylor flows, they will know that you can have a very nice, well-defined Taylor flow in channels to quite a large diameter, a few millimeters. What you start seeing from some point onwards is that some gravity is obvious. So you will see that the bubbles, the plugs, if it's bubbles, if it's gas, or if it's liquid, they will kind of sit closer to the bottom wall of the channel. So there is some effect of gravity, but is that as important? That's why it's a little bit subjective. Because they are still well-defined Taylor bubbles with a cylindrical body and the spherical caps and everything. So these are some criteria, but the main thing to remember is that gravity is not as important as surface tension. One thing as well, we talked a bit about mixing, and I will mention it here. We said that mixing in small channels, because we only have laminar flows, is due to diffusion. And there is this Fourier number, if people remember the reaction engineering, that is used to describe mixing efficiency. So we can have a diffusion coefficient, the time that the contact is happening, and the characteristic length of which the diffusion takes place. And we have good mixing. If people use micro mixers, as we will see, this is one dimensional number to check if good diffusive mixing will happen. So Fourier number has to be between 0.1 and 1 to have good mixing. So what I will do is that I will talk a little bit about mixing of single phase flows, and then we will be moving to two-phase flows. So I mentioned the mixers, and I'm staying a little bit more in those, because actually mixing, having efficient mixing, is where people have used, and in some of the references I have shown to you, I will show to you, there are industrial examples where people actually used micro-fabricated mixers, even in larger scale equipment, especially gases. So they tried to basically to reduce, to improve the mixing by reducing the spaces between, breaking the fluids down to improve the mixing efficiencies. But the rest of the equipment was a proper large scale. So micro devices is what one of the earlier applications, let's say, of micro engineering. It should be because this is the diffusion coefficient. Sorry?
Meter square per second, right?
I believe so, yeah.
P is time, meter square by length is meter.
Yeah.
What dimension?
Okay, I will have to check that. Yeah. Yeah, this is the dimension. It's meter per second. I think the diffusion coefficient.
Meter per second and then meter per second.
Yeah. Might be losing, maybe this is square. You're right. I can correct that. Yeah. I can check I can go back and check my notes. Sorry for this. Yeah, I can correct this. To make a note so I can remember afterwards. Thank you. So mixing strategies, we can do that by, and I have some photographs actually to make those a bit more specific. If we want to mix in micro scale, we can't depend on diffusion because our channels are small, but we can also, we want to mix two miscible phases, we can combine two different streams, or we can break one of the phases in one of the fluids in small substreams and put them in the mainstream of the other channel, or break also the other fluid in substreams. Which is this one. And then is this splitting and recombination approach to help reduce the thickness of the films and improve the diffusion mixing. So these are some schematics of the mixers. There is a lot of that in the literature. And as I said, people have used those from the beginning to actually try to improve mixing. For example, this one is it's very good for mixing gases. So this is, we have two inlets, two miscible fluids. We can combine the two fluids, and because the sizes are small, diffusion takes over and they will eventually mix. If we want to do it even better, we can split these two fluids into many substreams. One comes here, the other comes here, come like that. And then because they are broken into so many thin streams, they can mix much faster. Or we can have one of the streams broken down in many substreams, introduced into the other. People might have come across these herringbone structures. They're used a lot. What they do is you have some imaging here, different variations. You know, these herringbones can look one way or the other way, or have different angles. What they do is that they impose these sort of mixing patterns vertically, so from the channel upwards, and that improves mixing. This idea of split and recombine is also used a lot. We have used it. So these are results from some experiments we have done with LIF, where you basically have the two streams. If you leave them going parallel, it will take so long to diffuse, to mix by diffusion. What happens is that you can split those in smaller streams. And then again, basically this using mixers, inline mixers. And then again, over time, what happens is we break this lamella into thinner and thinner streams, so the diffusion takes over. It's much more fast. So this is in this case. And something else, mixing small channels. We mentioned that we have laminar flows, so actually it is it's more easy modeling. And these are some results we got from mixing two gases in methanol and oxygen in this case, in just a T junction, a T mixer. And even by playing around with the geometry of the mixer, the mixing can be improved. So this is what we plot here is the mass fraction. So this is one gas, this is the other. And when they are fully mixed, you get this gray color, which is half because they were joined.
Empty.
Initially, I have to remember how we started the simulations now. I think they started with empty channels, and then we went like this. So this is once it is a steady state. It's not the initial condition. But what you can do is that you can play, at that stage, we played a lot with the angle the channels join. Actually, this was not a bad one, just a standard T mixer. But you can have, let's say, variations of throttles here, because at this point here, we reduce a lot let's say, the thickness of the layers. Of course, this has to be also looked against the pressure drop that is imposed, because of course, if you have a throttle like this one, pressure drop is much, much higher. I'm sorry, it doesn't go down like this. Okay, so what I will do now, and as I said, this is more of an introductory lecture, just some concepts of microengineering and of intensified processing. There are I will mention a few things about gas liquid. Most of the subsequent lectures will be on liquid. But in gas liquid, we have different conductor types, and people have worked a lot with the film conductors, bubble or dispersed flow conductors, which is a little bit like the column, but much smaller bubbles, or foam conductors. Taylor bubbles might be something a lot more are familiar with, because there's been a lot of work done on that. In the film conductors, this is one of the earlier ideas, let's say, because it doesn't have a lot of microfabrication, is where it's like the chemical, the chemical process, the falling films. But in that case, we use microstructured plates to enable to have a thin film over which a gas phase might flow, a thin liquid film over which a gas phase might flow. And then the same idea with this one, but in case we could have the two phases separated by a mesh, so we avoid the mixing, we just let the diffusion happen, and which is easier also in the end to keep the two phases apart. If we have solids like catalysts in the mixture, if they are important, we can have the same as the film ones, the wall covered in catalyst. There are micro-packed beds. A lot of people have worked with those, because one good thing with the packed beds is that you can use commercial catalysts that have been tested. Because once you start fabricating different types of catalysts, for example, to cover a surface, then of course the catalyst properties might change, or the way the catalyzed reaction might be different, the mechanism might change. While with the packed beds, it's much more easy, because something has been tested can be applied directly. Yeah, wall-coated microchannels as well. And there are a lot of applications. There are some review papers. I mentioned one of them here. All these types of conductors and also the different reactions have been tested. And I just mentioned a few here, such as these direct fluorination of aliphatics or aromatics or heterocyclic aromatics, oxidation reactions, hydrogenations. But even in other, not just in reactions, in other applications, such as the gas liquid flows for nanoparticle synthesis. There's actually a lot of work on that currently, trying to use all these small channels for production of nanoparticles with very controlled sizes, evaporation as well. So not just reactions, but also a phase change. So liquid-liquid systems, this is also where we have worked a lot more. One of the main applications is solvent extractions, and I will be showing you a lot more examples later on that. Solvent extractions are used in a huge variety of industries, actually. Separation of biomolecules, was a mention of that in the morning as well. Pharmaceuticals are using a lot of solvent extractions. And there, not just there, but there it's also important to come up with solvents that are more benign, more environmentally friendly, let's say. So there is a lot more work, another area, let's say, of research to how to develop the solvents for the solvent extractions. They're used a lot for separation of metals. And this is where we are now currently doing a lot of work in my group. Critical metals, I don't know if you have come across them, and the whole problem with the critical metals. They're used a lot in all the renewables, of course, a lot in electronics, in magnets. And the problem is that if we go ahead with electrical cars, for example, or renewables like wind turbines, or then we need to have a lot more of these metals. And of course, mining is one way of getting them. Mining can be it can be challenging for the environment, but also it leads to depletion. So what needs to be done is actually to recycle and reuse metals that are already in operation. And solvent extractions are some of the main operations that are used for this recovery. They're used in spent nuclear fuel reprocessing as well. It's again a lot of solvent extraction there, but also for isotopes enrichment. So extractions is a physical process. But also in microchannels, people have done, or small channels, reactions for biofuel production. Again, taking advantage of mass efficiencies, improved efficiencies, fast mass transfer, polymerization as well. And this is the other area, emulsification. And we are going to be talking about that because one thing that we manage to have in small channels is to generate small drops of controlled or narrow size distribution, which is what you want when you do emulsification. Yeah, traditionally is done with, of course, mixing, high shear mixers, but we get a wide size distribution that, again, it can affect the properties. And what we want to do with micro fabricated channels is to create emulsions that have small sizes, drops with small sizes, and narrow distribution. So these are some of the areas. Emulsification is also used a lot for nanoparticle production. So again, by having these properties of the sizes, we can help the nanoparticle production as well. Okay, I will talk. Yeah.
That they some sort make interaction between each other. So can be studied.
What do you mean? Are they miscible or are they immiscible? Or are they miscible? It depends on what interaction and what can you measure. I mean, we'll talk a bit about measurement techniques, but in principle, yeah, I don't see why not. If it is the mixing that is of importance, it's one thing. If it's the reaction, again, you must
study. Unknown liquids are there, and they interact each other. And we want to study them.
Do you mean react, or what do you mean interact?
Interact, make interaction like hydrogen bonding can.
Okay, yeah. And then it all depends on what do you measure, isn't it? Or how do you measure what you need to measure?
What we need to.
Yeah, sometimes that can be in situ within your channel, and there are ways. Sometimes you might need to collect at the end of the channel to.
Sometimes
Yeah.
gas also interacts there, absorb on the surface.
Of the liquids, you mean? Yeah. Yeah, it's like in any channel, any stirred vessel reactor it would be. It's just that in that case, your conditions are better controlled because you along the channel, all your material will experience the same transformation, while in a mixer, in a stirred vessel, because of the non-homogeneity of the flow in the mixing, you may have different regions having a different. Of course, yeah, and it's always. I mean, some of the benefits we know about these microsystems is because we compare with what happens in larger, let's say, equipment or more traditional batch techniques. So what I have here is something I have taken from a classical paper, I would say, from Stankiewicz and Muline on process intensification. So we talk about small channels. People started using them for analysis, the microtask applications we mentioned. They then moved into microreaction engineering, but people don't just want to keep them in the lab, they want to actually go into production. And when we try to use small channels or microfabricated process units for production, we talk about process intensification. So what is process intensification? It was a concept that has been introduced some time ago. One of the pioneers, Ramshaw from Newcastle in 1995, introduced it as proposing that it means a reduction in the size of the plant and size of your process. But nowadays, intensification is not just size, although with the microfabricated equipment, we just do size, we reduce the size, but at the same time, we do other phenomena. So process intensification can refer to equipment. So we do reduce the size, but also the methods. How do we approach things? And the methods might be that we have multi-functional reactions. So reactors don't do one thing. You might have or hybrid separation, so where you combine a couple of different separations. Sometimes people to drive a reaction, they have the reaction and immediately remove one of the products, so it drives the reaction more. So this is about having a hybrid, let's say, unit operations. But because of the microfabrication, we are able now to do it. We use alternative energy sources, which might be more easy to do in scales as well. So instead of just having the traditional mixing, we could use ultrasound, microwaves, electrical fields. But again, they can be used in larger scale equipment. They might intensify a process. A lot of them are more easy to use in small microfabricated, precision engineered small scale equipment, or other methods like supercritical and some other green solvents. So process intensification, not just about size, is about methods as well. And we have this one as well, because it's a newer paper and it's a nice study. I have here a website also to have a look. These principles of process intensification. It's a series of books also, or of monographs that have been updated. So again, we discussed that in the very beginning for why do we want to do process intensification. It's much more nicely discussed here. We have to maximize the effectiveness of the molecular events. So we can alter the reaction rate by managing the frequency, energy, and timing for molecular collisions. When do we bring things in contact? We can do that in a more controlled way in a small scale. This is something that people have been saying a lot. We give each molecule the uniform experience within our process unit, within our reactor. This can be because we basically we reduce differences. We reduce what we mentioned, the gradients, either of temperature or concentration. So all molecules actually experience the same. In a stirred vessel, we may not have that. Optimize driving forces and specific surface areas. The surface areas is an example because we can have more specific interfacial areas, more surface area to volume ratio. And maximize synergistic effects, which again is, as I mentioned, we might be able to combine the reaction with the separation because that drives, let's say, the reaction. So this is a kind of interesting concept. When we talk about small channels, using them, or small equipment, using it for process intensification, in most of the times, this implies a transition from batch to continuous processing, which is also a different way of trying to design our processes. So a lot of the processes in traditional chemical engineering, you might have seen all this. One of the papers that suggested, I think it has it in the process intensification, that the traditional chemical engineering involved a lot of batch processes, mixers, and a lot of them are still used today. So the idea is that all these actually also mean that we might need to move away from this model to continuous processing, which is also having our processes happening in flow in channels. So this is a change of approach, and working in small scales enables that. And this is what I think, this is my last slide here, and I will stop. And this is what we will be discussing from now on. So I will stop. This is what I had for this first lecture, a bit of an introduction and some general concepts on why process intensification, small scales. We talked a bit about the mixing because this is something that even in large scale equipment, people might want to have the intensified mixing. And yeah, where do we come across it? So any questions?
Any industrialization or commercialization of the process intensified, or like